Hello, everyone. Welcome. Today, we're going on a journey back in time to explore something truly remarkable. How ancient civilizations, without the benefit of modern technology, figured out the size and shape of our Earth. Forget satellites and GPS for a moment. We're talking about ingenuity, observation, and a healthy dose of geometrical brilliance. Get ready to have your mind blown. We'll be starting our journey in ancient Greece, which is where a lot of the groundbreaking work on measuring the Earth was done, and then we'll jump to some other cultures as well. Let's start with the basics. Why bother measuring the Earth at all? For early civilizations, it wasn't just about satisfying curiosity, although that certainly played a part. Understanding the size and shape of their world was incredibly practical. It helped with navigation, map-making, and even predicting the seasons. Accurate maps were essential for trade and exploration. Knowing the Earth's dimensions allowed for more precise calculations of distances, making travel safer and more efficient. Even predicting when to plant crops was related to the Earth's orbit. Now let's dive into the star of our show, Eratosthenes. This Greek scholar, living in Alexandria around 240 BC, is credited with the first accurate measurement of the Earth's circumference. His method was surprisingly simple, relying on observations of shadows and a bit of geometry. Eratosthenes was the chief librarian at the Library of Alexandria, one of the largest and most significant libraries of the ancient world. The library was a treasure trove of knowledge, attracting scholars from all over the Mediterranean world. Eratosthenes had heard about a curious phenomenon in the city of Syene, modern-day Aswan, in Egypt. On the summer solstice, the longest day of the year, the sun shone directly down a well, meaning objects cast no shadow at noon. This suggested that Syene was located directly on the Tropic of Cancer. The Tropic of Cancer is an imaginary line on the Earth's surface where the sun is directly overhead at noon on the summer solstice. Imagine that! No shadows. But Eratosthenes noticed something different in Alexandria, located much further north. On the same summer solstice, objects did cast a shadow. He reasoned that if the Earth were flat, objects would cast the same shadow in both locations. The fact that they didn't mint the Earth must be curved. This was a crucial insight, establishing the Earth's spherical nature and paving the way for his measurements. Here's where the geometry comes in. Eratosthenes measured the angle of the shadow cast by a tall obelisk in Alexandria on the summer solstice. He found that the angle was about 7.2 degrees, which is approximately 1/50th of a full circle, 360 degrees. This meant that the distance between Alexandria and Syene represented 1/50th of the Earth's total circumference. Simple so far, right? The next step was to determine the distance between Alexandria and Syene. This was estimated to be around 5,000 stadia, an ancient unit of length. The exact length of a stadium is debated, but scholars believe it was roughly equivalent to 157.5 meters. This estimation would have involved land surveys, a dangerous occupation, and potentially inaccurate. Now, the final calculation. If 5,000 stadia represented 1/50th of the Earth's circumference, then the entire circumference must be 50 times that distance. That's 5,000 stadia asterisk 50 equals 250,000 stadia. Converting that to meters using the estimated stadium length, Eratosthenes calculated the Earth's circumference to be roughly 39,375 kilometers. How accurate was Eratosthenes' calculation? The modern accepted value for the Earth's circumference at the equator is about 40,075 kilometers. So Eratosthenes was off by only a few percent. Considering the limitations of his tools and methods, this is an absolutely incredible achievement. It speaks volumes about his intellect and the ingenuity of the ancient Greeks. Eratosthenes wasn't alone in his pursuit of understanding the Earth. Other ancient Greek thinkers, such as Aristotle, also contributed to our knowledge of the planet's shape and size. Aristotle provided several arguments for a spherical Earth. He pointed to the changing constellations visible as one travels north or south. The fact that different stars appear above the horizon as you move to different latitudes suggests a curved surface. Aristotle also observed the shape of the Earth's shadow during a lunar eclipse. The Earth's shadow cast on the moon is always round, regardless of the Earth's orientation. This wouldn't be the case if the Earth were a flat disk, which would sometimes cast an oval or linear shadow. This observation strongly supported the idea of a spherical Earth. Beyond Greece, other ancient civilizations also made significant contributions to understanding the Earth. In ancient China, scholars were developing sophisticated maps and astronomical observations. While the Chinese initially believed the Earth was flat and square, resting under a dome-shaped sky, by the early centuries AD, they too began to adopt the concept of a spherical Earth. Chinese astronomers, like their Greek counterparts, used celestial observations to infer the shape of the Earth. They meticulously tracked the movements of stars and planets, noticing variations in their visibility depending on location. These observations eventually led to the acceptance of a spherical Earth model, albeit sometimes with variations on the Greek understanding. The Jubi Suanjing, an ancient Chinese mathematical text, contains discussions about measuring the height of the sun using gnomons, vertical rods that cast shadows. While initially used for calendar calculations, these techniques could also be applied to estimate distances and infer the curvature of the Earth, similar to Eratosthenes' method. In India, ancient mathematicians and astronomers also made remarkable progress in understanding the Earth's dimensions. Aryabhata, a 5th-century Indian mathematician and astronomer, accurately calculated the Earth's circumference and even proposed that the Earth rotates on its axis. This was centuries before Europeans came to the same conclusion. Aryabhata's work, documented in his treatise Aryabhatiya, included precise calculations for the Earth's circumference, diameter, and radius. He also developed sophisticated trigonometric functions, which were essential for astronomical calculations and surveying. His contributions were truly groundbreaking for his time. The concept of latitude and longitude, crucial for creating maps and navigating the globe, was also explored in ancient times. While rudimentary versions existed earlier, the Greeks, particularly Hipparchus, significantly refined the system. Hipparchus developed a coordinate system based on lines running east-west, latitude, and north-south, longitude. Determining longitude, however, proved to be a much greater challenge than determining latitude. Latitude could be relatively easily calculated by measuring the angle of the sun or certain stars above the horizon. But longitude required knowing the time difference between two locations, which was difficult to accurately measure without precise timekeeping devices. The development of accurate clocks, particularly the marine chronometer in the 18th century, finally solved the problem of accurately determining longitude. This invention revolutionized navigation, making it possible for sailors to pinpoint their location at sea with unprecedented precision. Before then, many ships were lost at sea due to lack of longitude. Early map-making was, of course, limited by the knowledge of the known world. Maps were often centered on the map-maker's own region, and areas further away were depicted with less accuracy. However, these early maps provided invaluable information for trade, exploration, and military campaigns. They also served as a testament to humanity's desire to understand and chart its environment. The accuracy of early maps also depended on the surveying techniques available. Ancient surveyors used tools like gnomons, plumb bobs, and measuring chains to determine distances and angles. These tools, while simple, allowed for surprisingly accurate measurements, especially over short distances. Interestingly, the shape of the Earth wasn't always a settled question. In some cultures, the idea of a flat Earth persisted for centuries, even alongside evidence suggesting otherwise. This highlights the power of established beliefs and the challenges of changing deeply ingrained worldviews. It shows how important it is to always check for evidence before believing something. Even after the spherical Earth model gained acceptance, there was still debate about its precise shape. Some speculated that it was perfectly spherical, while others suggested it might be slightly flattened at the poles. It wasn't until the 18th century that Isaac Newton proposed the idea of an oblate spheroid, a sphere flattened at its poles due to the Earth's rotation. Newton's theory was later confirmed by measurements taken during expeditions to different parts of the world. These expeditions, often involving difficult and dangerous journeys, provided crucial data that supported Newton's model and further refined our understanding of the Earth's shape. So, what lessons can we learn from the ancient science of measuring the Earth? First, it shows the power of observation and critical thinking. Eratosthenes, Aristotle, and other ancient scholars didn't have access to advanced technology, but they used their intellect and the available tools to make groundbreaking discoveries. It also highlights the importance of collaboration and the sharing of knowledge. The exchange of ideas between different cultures, from Greece to China to India, played a vital role in advancing our understanding of the Earth. Even today, scientists all over the world must work together to achieve great things. Finally, it reminds us that scientific progress is a gradual process. Our understanding of the Earth has evolved over centuries, built upon the work of countless individuals. Each generation has added to the knowledge base, refining our models and pushing the boundaries of what we know. The quest to measure the Earth continues to this day, with ever more sophisticated tools and techniques. Satellites, GPS, and advanced surveying technologies allow us to map the Earth with incredible precision, revealing details that were unimaginable to ancient scholars. From Eratosthenes' simple observations to the complex measurements of modern satellites, the journey to understand our planet has been a remarkable one. It's a story of human curiosity, ingenuity, and the enduring quest for knowledge. This has been a long video, and if you learned anything about the ancient science of measuring the Earth, maybe subscribe and hit that like button to help others learn more too. And as we look to the future, one thing is clear. The pursuit of scientific understanding will continue to drive us forward, leading to new discoveries and a deeper appreciation of the world around us. Always remember the ingenious minds who shaped our understanding of the Earth using only shadows, angles, and a thirst for knowledge. Be curious, think oddly,